Hello everybody, it's Micah Wiersma here today to talk to you about Plan B, Mobilizing to Save Civilization by Lester R. Brown. My chapter that I'm focusing on today is Stabilizing the Climate and Shifting to Renewable Energy. In this chapter, Lester Brown kind of outlines how he sees the future of the sustainable energy economy, moving from oil, coal, and gasoline, and even natural gas, to wind, solar, and geothermal. That's basically the entirety of the chapter. To start with, he starts listing a lot of large projects that were going up in 2008, kind of showing the sign of the times on how the energy economy was going. Since then, there have been a lot of changes, so I've tried to update them going forward. The first sustainable energy that he gets into is wind, and he puts a lot of importance on it. Wind is the centerpiece of the Plan B economy. In his final draft of the future of energy policy for the world, in the way that he outlines it, it accounts for more than half of the world's sustainable energy output. The pros of it are very good. Wind cannot be depleted. It's low cost. It's widely distributable. The dual use of land is a big focus in the past couple of years. Farmers can put it on their land and still farm the land. It doesn't interfere with them in any reasonable way. The cons are somewhat minimal. They fluctuate by location and time. Energy can be produced far away from cities. That's where sometimes the best wind conditions are. Upfront investment, but what's new for sustainable energy? Sound and visual annoyance and possible damage to wildlife, which have been mostly proven, partially by Brown, partially by online sources, to not be big of a very large problem. Now the capacity, as Brown puts it out, harness 1/5 of the world's energy power through wind would provide energy for about 7 Earths. It's very, it takes a lot of work to harvest that amount of energy, but a lot of the other ideas of how much we can get out of wind energy is very, very positive. Here you can see some of the main areas of interest in the United States and Australia. The purple on the United States diagram is around 9.59 meters per second. In Australia, that red is 10 meters per second. So those are pretty comparable in speeds and possible outputs. You can see that United States Midwest, kind of the sweeping plains as we know them, alongside the mountains, which also sometimes allow more elevation so that you can get more wind. Those are optimal conditions for this type of sustainable energy. Australia, however, accounts for a lot of the energy that they can get from the sea, and we'll get to that in a minute, but you can see that a lot of the coastal winds coming from across the ocean give Australia a really good advantage. Aggressive offshore development could power Europe by 2020. That's Brown's estimate. And a lot of the interesting things up and coming over there have proved that it could be possible. China now leads the world in wind with 180,000 megawatts produced in 2017. That's kind of an update from Brown's updates that he gives in the book. He says that the US is leading and China is up and coming. That was in 2008. We're living in different times now. This information to the left was acquired from GWEC, which is the Global Wind Energy Council. They gave a lot of good information on 2017 statistics towards wind power. You can see here Asia taking about 1/3 of the pie, 42%. Coming up shortly after is Europe and then North America. Those are the big three in wind, because it's very popular in developed nations as a supplement to other sustainable energies. But like Brown says, it's a very up-and-coming system. The world gained 52%, 52,500 from the last year. How does this relate to Brown's estimates on what we need? Sorry about that. 3 million megawatt generating capacity by 2020, covering about 40% of the world's needs, requiring about 1.5 million turbines. And of course here he starts getting into, is this possible? Yes. Look at the production that we have for other systems. Look at automobiles. Look at how we've changed the production of technology year after year in the past century or so. Every time a new technology comes out, we need to create a new processing system to create it. We can do it for sustainable energy, just like we did with cell phones, just like we did with laptops, just like we did with World War II airplanes. If we mobilize with urgency, he says. The next sustainable system that he gets into is solar. We know solar energy is abundant. I mean, that says a lot about just what we're, look up in the sky. There you go. Feel it on your hand. That amount of energy and warmth is hitting the entire world, a large portion of the world at all times. The pros is it cannot be depleted, until the sun goes out. Virtually undepletable. Low maintenance, easily attached off-grid. We'll get to that in a minute. The cons are weather dependent, and this leads to some storage issues. You need to be able to hold on to the energy for 8 hours and slowly dole it out to the population at night when you can't get any more energy. So what do? You need a battery, and our battery technology isn't so advanced that we can easily hold on to that large amount of energy for that amount of time. We're getting better though. High land use. It's not as easy for some of these larger solar farms to plant anything underneath them. It's a lot easier to put them out in the middle of nowhere, where in the desert, where people don't want to live usually anyways. And rare earth metal use, that's just kind of acknowledging that the materials that these are made of sometimes are not sustainable. People are working on that. People are working on making them more efficient so they don't use up as much rare earth. But what can you do? To the left, a little interesting thing. That's Rolleman's Beta-Ray tracking solar panel. And it's kind of a large crystal ball, and you can't quite see it in this one, but you can see the reflection of it. On the opposite side, there's a solar panel taking in focused sun that tracks across the sphere to always be in the sun's focus. So all you're moving is a tiny little solar panel, but you're getting the entire focused energy of the area of the sphere, which is very efficient. Not quite cost efficient yet, but it's a very interesting step forward. Brown again gives a lot of estimates from 2008, 2009. And they're all very interesting. I give them below, but I think this one more recently says it all. This map to the left, you can see kind of the output for solar in different places just based on flat solar panels. Most places have, solar panels angled towards the sun depending on the climate. Other places might even have tracking technologies so that it can move during the day, but here we're just talking about flat solar panels. The black dots in this image would be enough to supplant our current primary energy suppliers: coal, oil, gas, nuclear. Basically, if we put solar panels over those 6 black dots, the Earth wouldn't have no need for fossil fuels. We could supplant them with solar energy right there. And it even gives the locations, which I've listed below, all in unpopulated desert areas, kind of moved evenly across the globe. This system would require a pretty large grid to pull off, but we're creating those for other systems anyways. So if we create large-scale grids across the world to move around sustainable energy, then just these places could give us all that we need. new facilities are outfitting themselves, with new energy storage systems, and we keep getting better in that regard. Brown says that the U.S. has enough space to provide for itself 4 times over with solar, just unused space. Brown mentions a 1,000 megawatt facility planned in China, and today the Tengar Desert Solar Park alone produces 1,500 megawatts, and they're only expanding. This gets into one of the pros of solar energy, the ease of which it can reach desolate, not quite desolate, but remote communities. Brown gives a short blurb on India and its use of kerosene lamps and how it's slowly sometimes being supplanted by a solar panel. He even gets into how it's actually a viable economic decision for them to get rid of the kerosene lanterns and replace them with solar panels. They're just so accessible, they can be installed almost anywhere and hooked up to whatever couple of appliances that people need. It's a wonderful way to get energy to people in rural communities, kind of areas that their carbon emissions are spread out instead of all concentrated in one place in the city. Instead of creating an entire grid to reach every single one of those people, you can have these things that work off the grid that you can give straight to them and they can start working right away. The bottom line for energy solar, Plan B notes current 2020 goals for solar at China and all these other countries. These are kind of the big 4, I believe, at the time of his writing for pledges towards solar. Middle East might have made more strides since then, we'll see. Total production of 1,100 million square meters, producing 1,100,000 megawatts. That's a pretty large portion also of his energy goals for 2020. We'll see the breakdown at the end. The next system that he gets into is geothermal. The blurb that kind of impressed me straight away: the heat in the upper 6 miles of the Earth's crust contains 50,000 times as much energy as found in all the oil and gas reserves combined. That's of course based off of large-scale estimates, but I'd say the entire surface of the Earth, 6 miles down, is probably going to have a lot of energy in it. Pros: it's renewable, not quite like we've said with the other ones, they're not quite undepletable, since you can mismanage one, and although you're not removing a geothermal hotspot, you're kind of removing the resources around it that help you tap it. Water, dry rocks, anything like that. If you have a bad accident, you might remove some of the potential for that area. A big pro that Brown talks about a lot is direct heating. You don't have to convert it into energy immediately. It doesn't have to all go into electricity. You can simply pump hot water into your floors and heat your house that way. You can pump them into your bath. You don't need to take it into an electrical plant, move it into a grid, and then use it to heat your bath. It's direct. It's low land usage. It's one of the lowest land usages of any of these. And it's extremely dependable. The Earth doesn't get cold. Pressure stops it from cooling down. So the core will always have enough pressure to keep the rock molten until an indeterminable amount of time. Destroys the Earth in some way. Cons: it's ultimately location dependent. You want to be on top of a volcano. We'll see a map of that in a minute. It has a high upfront cost, perhaps higher than the other 2 that we've seen. You need to dig low. There are some options where you can dig a little bit shallow, but it's not going to be as efficient of a system. And water use. Some of the issues for the surrounding environment have been infrequent earthquakes, possible, just about the usual things that you get when you drill deep into the Earth. And it uses a good amount of water, which a lot of sustainable systems try to avoid since it's a precious resource. To that right is that map I promised you of some of the volcanic hotspots that create geothermal activity, possible tapping areas. Brown cites Iceland in the book as receiving 27% of its power from geothermal. But today, it's 53% from geothermal, and they are now 100% supplied with renewable energy. The influence of geothermal is that it creates cheap heating, allowing for easy applications like floors, baths, and greenhouses all year round. Brown puts a lot of emphasis on the greenhouses because it's a really interesting application. I've looked at it in past classes. Essentially, you hook up this warm air, whatever pipes are heating your house, you just run one out to a planter outside or inside a greenhouse, and you can plant all year round. It keeps that heat. It's a very natural way of doing it. You're not using some exorbitant energy cost to keep your greenhouse warm. It's just from the earth. Larger power plants are working on more efficient ways of using this. The old way was just kind of regular steam turbine, kind of in the same realm as coal plants work, where it's converted, heat is converted into steam through pressure, and then that's used to spin a turbine. Lately, they've found more ways to manipulate the pressure that they're doing at to immediately turn it into steam faster and faster, quickly creating large amounts of energy to harvest. And there are also other systems that kind of slowly heat up. These are slowly up and coming, and they're used for less extreme hotspots. Those pictures to the left there are of Iceland plants. There's a local spring that they've kept working while they're harvesting the geothermal energy. Those are very warm and active hotspots. A lot of the future sites would probably not be this way. We'll probably get down to less desirable sites that we need to harvest more slowly or more carefully. Plan B estimates Japan and the US alone could produce 240,000 megawatts, potentially. Therefore, the goal is set at 200,000 megawatts by 2020. The nearly 11,000 megawatts in U.S. plant-based electrical generation comes primarily from burning forest waste. Plant-based electrical generation is a strange beast. It's not exactly really recommended as much anymore. There are some ways that they've made it still work, and they still are a net gain for society and for sustainability as well. We'll get to those cons in a second. The pros: it's garbage. It's just there. We want to get rid of it. It's always local. It's always nearby. We're always creating garbage. Why don't we burn it and create new energy for ourselves? It's renewable because we're always making garbage. And it replaces fossil fuels with similar tasks. Biodiesel, which we make from crops, which is, I believe, explored in other chapters thoroughly, can be used in lieu of gasoline or oil. It's nice and effective. Wood waste is kind of replaced for coal. Coal plants, burning wood waste, it's not as efficient, but when it's something that's not going to be used anymore, it's just as well. And methane for natural gas, which is actually harvested from landfills. And I've seen a couple of these taps around. In fact, I believe, no, not in this one, but the top left picture is a methane harvester for a landfill in a third world country. The garbage decomposes, it releases methane into the air, but this captures the methane and then uses it as fuel. The cons is it's not an ultimate solution to waste. There are much better solutions, such as going full recyclable plastic or paper or cardboard, where it's always renewable and it's always recyclable. This does, in many forms, release pollutants, and there's a note on the next page. In fact, it pertains to this and the expensive transport, where Brown explores the viability of this option. A third report published in Science indicates that burning cellulosic crops directly to generate electricity to power electric cars yields 81% more transport miles than converting the crops into liquid fuel. Basically what that's saying is it's going to be it doesn't make up for the trouble that it is to process this stuff in large quantities. Basically the only uses it's going to get is in local sizes. The more research is done on liquid biofuels, the less attractive they become. That's also straight from Brown. The bottom line for his projections, though: forest, urban wood waste, switchgrass, replaceable trees, all kind of junk plants that will replace themselves immediately. The U.S. could develop 40,000 megawatts by 2020. The world could handle 200,000. That's not bad, especially for it being waste. Hydropower. Roughly 60% of the world's electricity comes from hydropower. That's pretty good for something that you don't really hear as often in the sustainable circles anymore. You can see here the pros. It's renewable, it's dependable, and it's a staple for remote communities. You'll see a couple African communities, or African countries, some remote ones, stating that they have 100% renewable, while a large portion of that is going to be from hydropower. Many African countries might be in tall, very high elevation floodplains with many waterfalls and rivers and lakes that could be harvested for hydropower. The cons are environmental damage and high upfront cost. The environmental damage comes in many forms: the risk of floods, ecosystem effects. It kills off certain kinds of fish that need to go upstream. It kind of isolates different ecosystems from each other, which is not very good for biodiversity. And there's also this effect where when they drain a river to create the dam, all the biomass at the bottom of the river dries up, releases methane in large amounts for some of these larger projects. Something like the Hoover Dam, you can only imagine how much water that displaces and how much disruption it causes to the ecosystem. However, Brown comes away from hydropower in the form of rivers and lakes a little bit as he starts talking about tidal and wave forms of harvesting energy from the water. In 2015, more than 70% of Brazil's generation was from hydropower, much of it from its rivers, some of it from its oceans. Currently, the Sweha Lake Tidal Power Station in North Korea is the highest output. These are the types of stations that are placed along kind of at the edge of inlets in the land. The water rushes in with the tide and it rushes out of the tide, and as long as you can bridge much of this space, then you're getting all that energy from the water coming in and then coming back out. So it's kind of, when it goes either way, it's more like a river than the ocean. It's one large-scale movement. Now these smaller scale projects that harvest wave energy are a little bit different. They're getting a little bit of energy from each wave, kind of this kinetic energy of the ocean. That down there is the Lewis Wave Energy Farm, which outputs about 40 megawatts. That's kind of small compared to all the other projections that we've seen so far, but when you see the size of it and how it can be plopped just about anywhere, you start thinking about the implications. Larger scale projects are shooting for 500 megawatts in larger farms. Capacities for wave farms is projected to be 10 million megawatts worldwide. But of course, there's a lot of ocean to harvest, and there might be better ways to get the energy than that. The bottom line, Plan B predicts 90 945,000 megawatts for hydroelectric power in operation worldwide in 2008. Will expand to 1,350,000 megawatts by 2020. Of this, it is projected the U.S. could produce 400,000 megawatts. That's a pretty nice sum. And from what I understand of the current situation with sustainable energy, it's looking to be one of the more holistically accepted of everyone. And many of the reforms coming up, hydropower looks like it can survive some of the cuts. We're moving into the conclusion now of all this. Plan B's total of 5,300,000 megawatts by 2020 would be enough to replace all coal and oil and 70% of natural gas. Solar heaters and other methods could drastically reduce the energy needed for heating homes and other large-scale energy uses in society. Brown again cites wind as producing a large amount of the world's energy. You can see the breakdown below there. Wind, 30,000 compared to rooftop solar electric systems as 1,400 solar power plants. I think Brown maybe should have been thinking about more solar power plants. I know that the battery power isn't going up very much, but it seems like it's really advancing fast at this stage. Geothermal, hydropower, and solar thermal power plants bring up the rear. That seems good enough. Hydropower is pretty up there with that large amount, just because it's such a nice untapped resource that we are making a lot of advancements in. Thermal energy capacity brings in geothermal and biomass, solar rooftop water as well. You can see that total coming out to so and so many gigawatts, which a lot of the different values in this chapter went from gigawatt to megawatt. I've converted most of them, almost all of them, to megawatts, just for understanding's sake, so that we could compare all the numbers in these slides against each other. The conclusion here for the U.S. is the breakdown to the bottom left here. You can see coal, oil, natural gas, and nuclear mostly being phased out. I believe Brown mentions more nuclear plants probably going out of style and being decommissioned in the future, although I understand that decommissioning them is a pretty big task. He has a short blurb on how he doesn't really include nuclear in these projections just because of some of the downsides to them. You have nuclear waste, decommissioning the entire thing, and security against terror and other threats to security, insurance for the plant. Those things make nuclear not viable in his mind. Now, I understand that there are still advancements in nuclear going on, but I think that his critiques still ring true and could be a big concern in the future. As for Brown's vision for America, lines between Canada, California, and Dakotas and the rest of the country are already being looked at. They're already being planned and projected by different companies. If, for instance, some of the large wind farms in North and South Dakota, which we saw earlier, were in a very nice position for wind generation, if those could be picked up and just zoomed around the Midwest via lines, then places like Michigan and other parts of the country might be able to get some of this energy without being in that position of environmental kind of privilege. Supergrids, Brown talks about different ones being proposed and looked at around the world, things like entire grids going all the way from the Arabian Desert to Europe, sharing together geothermal, wind, and solar energy from each spot that kind of has a focus on it. Other countries like India and Australia. Iceland is talking about running cross-continental cables along with a couple other countries so that we could share energy across continents, across the ocean. So how do Brown's wildest hopes line up with where we're at in 2018, 2 years from the goals that he so desperately wants to meet? Well, he does mention at the beginning of this chapter that his projections aren't based on what they can do, it's based on what they need to do. It's based on what the needs of our future ecological situation depends on. But looking at where we are now, I'd say we can optimistically look at new benchmarks. In 2015, share of energy from renewable resources and gross final consumption of energy in the European Union reached 16.7%, nearly double the figure from 2004, 8.5%. EU countries have already agreed on a new EU renewable energy target of at least 27% by 2030. 11 countries have met these targets. Despite pushbacks and recent reforms, the Morgan Stanley analysts said in a report, we project that by 2020 the renewables will be the cheapest forms of power generation across the globe, with the exception of a few countries in Southeast Asia. In that case, in a way, Brown's vision is being met, that it's going to be economically viable for all of these systems to supplant the old systems. What they will need to overcome is things like the sunk cost fallacy, which state that if I already have my money in this type of energy generation, I don't want to switch to another energy generation because I've already put my money into this energy generation. That is the kind of thinking that needs to be removed or fought against for this kind of change to come about. That's what we're hoping to do when we educate other people on these types of issues. Thank you for listening. That is my lecture. I bid you a good night.